Hello everyone, let's solve some Leetcode today. So today we have Leetcode 110, that is balanced binary tree. In this problem we will be given a binary tree and we have to determine whether it is height balanced or not. So what is a height balanced binary tree? In a height balanced binary tree, the absolute difference between the height of left subtree and the right subtree is less than equal to 1 for each and every node present in the tree. For example, here we have the root node 3. Now we have left subtree and then the right subtree. So what is the height of left subtree? We only have one node here, so it is 1. And what is the height of right subtree? So on the longest path here, we have 1 and 2. If you go in this direction, we also have 1 and 2. So at most, the height of the tree is 1 and 2, that is 2. So now let us try to figure out the difference between the left and right subtree. So the absolute difference between the left and right subtree height is equals to 1 minus 2 absolute is equals to 1. So for this node, this particular condition is satisfied. Now let us look at the ninth node. So what is the height for left subtree? It is 0. What is the height for right subtree? It is 0. So absolute difference between left and right subtree for 9 is 0 minus 0 is equals to 0, which is less than equal to 1. So this node also satisfies this particular condition. Now let us look at this node 20. So what is the height of the left subtree? Well, it is 1 because there is only one node. What is the height of right subtree? It is also equal to 1 because there is only one node. So what is the absolute difference between the left and right subtree? It is equals to 1 minus 1 equals to 0. So this node 20 also satisfies the condition for the balanced binary tree. And similarly, node 15 and node 7 also satisfy this condition because their right and left subtree heights are 0. So their difference will be anyway 0, which will satisfy the condition. So we can confidently say that this tree is balanced binary tree. Now since we have to go to each and every node in the tree, we have to figure out the difference between the left and right subtree for that node. We are going to use a simple algorithm DFS. So we can start with our result variable equal to true. It means we are assuming in the starting that the given binary tree is in fact a balanced binary tree, and then we will use DFS to verify it. And if during the DFS at any point we figure out that okay, this particular node does not have the difference between left and right subtree less than equal to 1, we know right then and there that this is not a balanced binary tree, and then we will simply change the res variable to false. So now let us look at the workflow. So first of all, we will be at the 3 node and then we have to figure out the left and right subtree height. So we will try to first of all figure out the left subtree height. So we will go here and then we reach 9. Then on the 9 we also have to figure out the left and right subtree. So we will go from 9 to left subtree and this is none. So this is the base condition. From here we will simply return 0 because none does not exist, so we return 0. So the left subtree height is 0 and then we will go here. Here also we have none. So this is also a base condition. So we will go back and we will simply return 0. So we have left subtree height equal to 0 and right subtree height equal to 0. Now before we go back to the 3, we will initially check for the 9 itself. Is 9 a balanced binary tree? Well, simply we will check is L minus R less than equal to 1. Then we see that okay, 0 minus 0, yes, it is definitely less than equal to 1. So we can say that 9 is properly balanced. And now we have to go back to 3 with the height. So which one is going to be the height? Is it going to be the left subtree or right subtree? Well, simple. We are going to take the maximum between left and right subtree. And currently they are both 0. So we will simply take 0 and we will add 1. Why are we adding 1? Because of this 9th node, we are counting the 9 also in the height now for this 3. That's why we are adding the 0 plus 1. So the left subtree height for 3 is equals to 1. Now we have to go to the other branch. That is on this branch, we have to find the right subtree height. Then we go to 20 and 20 also we have to figure out the left and right subtree. So here's the left subtree, here's the right subtree. Let us go in this direction. We reach 15. Now on 15 also we find that okay, this is none and this is also none. So we simply return 0 and 0 from here. We got 0 here, we got 0 here back. Then we will check is this particular node is properly balanced or not. We see that the left is 0, right is also 0. So we know that left subtree height minus right subtree height is equals to 0, which is less than equal to 1. So this 15 is properly balanced binary tree. Now we will take the maximum of L or R and then we will add 1 into it and return. Since they are both 0, so we will simply return like this 0 plus 1. Now we are counting the 15 for the left subtree height of 20. So left subtree height of 20 is 1. Now we are going to go in the next direction, that is for the right subtree. So we will go in this direction and then we find 7. For 7 also we have none here and here also we have none. So for this also we are going to get 0 and 0 back and we will check this particular node also, is this balanced? Then yes, we see that it's 0 and 0. 0 minus 0 is going to be 0 and it is going to be less than equal to 1. So yes, this is also balanced binary tree. Then we will take the maximum between these two heights, we will add 1 and then we will return it back. Since both of them are same, so then we will again send back 0 plus 1. We are adding 1 to count for 7 also now. So the height of the right subtree is going to be 1. And now we have the right subtree and left subtree for 20. So we are are going to check 20. Is 20 a balanced binary tree? Well, we have L equals to 1, R is equals to 1. Now the absolute difference between L minus R is equals to 1 minus 1 is equals to 0, which is less than equal to 1. So yes, the node 20 is also balanced binary tree. Now we will take the maximum between the left subtree and the right subtree height, and we will add 1 to count for the 20 node, and then we will send it back to 3. So we are going to do this 1 plus 1. This one is coming for the 20 node. We are now counting this particular node also for the height for 3. So now the right subtree height for 3 is going to be 2. Now we have the left subtree height and the right subtree height for 3. Now we are going to check this 3. Is this balanced binary tree? Well, let us figure out. We have L is equals to 1, R is equals to 2. Then the absolute difference between L minus R is going to be 1 minus 2. The absolute will be simply 1, which is less than equal to 1. So this also satisfies the condition properly. So it means the node 3 is also proper balanced binary tree. And since we have gone through all the nodes now, so our DFS will simply return and end. And once the DFS has ended, we will simply return the res variable. And since we did not find any node that was not satisfying the condition for balanced binary tree, we never changed the value of the result variable from true. So it means we will end up returning true, and that will be the right answer. Now let us take the same example again, and we are going to start from 3 again. In this time, we are going to assume that 9 does not exist. So we don't have this 9th node. Instead, we have a none node. And the height for this none node is going to be simply 0, right? So when we are calculating the height, we know that from here we will get a 0. So the left subtree height for 3 this time is going to be 0. And we have already calculated above that from here, this tree, the right subtree height is going to be 2. So the R will be 2. Now let us check if 3 is balanced binary tree or not. So we have R is equals to 2, we have L is equals to 0. So the absolute difference between L minus R, that is left subtree minus right subtree height, is equals to 0 minus 2 is equals to 2. Now we are taking absolute value, so we are just removing the negative sign. But we can see that 2 is not less than equal to 1. So this condition is now invalid. And that's why 3 does not make a balanced binary tree. Which means at this particular position, when we are checking it, we will set the rest to false. And once we set the rest to false, we know that the tree is not balanced binary tree. We will just return from here and then end the function, and then we will end up sending back this result variable, the updated value. So false will be returned. And so that's how you solve this problem. Now let us go through the code also. We have the result variable equal to true. We are assuming that the given tree is balanced binary tree from the starting. Then we are defining our DFS function here. So in the function, first of all, we are declaring that we are going to use a variable rest, which is not local to this function. We are taking it from outside the function here. And now we have a few base conditions. So in case we find that the res is false, we are directly going to return 0 because we know that the tree is not balanced binary tree. This condition will hit if at any moment we set the res to false and then we return back and we go to some other branch in the tree. So instead of going through the entire tree branch, we are just going to say that, hey, if the res is already set to false, why are we going through the next tree branch anyways? Let's just return early. And here we have another base case where we are checking whether the node is none or not. So if the node ever becomes none, we know that the height of the none node is going to be 0. So we simply return 0. So if they do not hit, we know that we have nodes to traverse. So here we are calculating the left subtree height and then right subtree height. So for left subtree height, I'm just calling the DFS function recursively on the left node, and then I'm calling the DFS function recursively on the right node for right subtree height. And here at this point for this current node, we are checking the difference between left subtree height and right subtree height. If the difference is greater than 1, that means the difference is 2, 3, 4, 5, something else, we know that we found a node that does not satisfy the condition. So it is not a balanced binary tree. And so we are setting the rest false and we are returning 0. We are not returning height or anything. We are simply setting the rest false so that later on for any other branch, the rest will be false, and for any other branch, this particular condition will hit and we will early return from that branch. We will not go through entire nodes for that branch. Now if this is fine, we know that the tree is balanced binary tree, so we do not set rest to false and we simply return the height. So we will take the maximum of left subtree height or right subtree height, and then we will add the one for the current node, and then we will return it to the parent node. Simple. So our DFS function completes here, and here I am calling the DFS function and passing the root of the given tree. Once the DFS function completely runs, we can simply return the rest. So now let us run it and see what happens. So yeah, it runs in 0 milliseconds and beats 100% of the solutions on Leetcode. So just don't trust this number, but yeah, it is a pretty efficient solution because we are early returning. We have a base case where we are checking whether the res is false or not, and then we are early returning, saving us extra computation time. Now let us look at the time and have space complexity for this particular solution. So in case each node in the tree is completely height balanced, we will end up traversing through all the nodes in the tree without ever returning early. So that will result in the worst case time complexity to be order of n, because we are going through each and every node in the tree once. Now you might have expected this to be the case, but I'm sure that you have a question that why, Satyam? Why is space complexity equals to order of n? Because we are not using any extra variables, we are not storing anything in the array, we don't have a hash map, we did not initialize any data structure. So why do we have order of n space complexity? And my answer to you is very simple. This is for auxiliary space. So this space is basically referring to the call stack. Since we are using a recursive function dfs, that is going to have a call stack, and in the call stack we will have multiple instances of dfs function running: dfs1, dfs2, dfs3, dfs4. And if our tree is something like this: 1, 2, 3, 4, 5, then once we start from here, we will store dfs of 1 here, then we will store dfs of 2, then we will store dfs of 3 here, we will store dfs of 4 here, we will store dfs of 5 also on the call stack somewhere here. So we end up storing the dfs calls for all these nodes, the n nodes. So the call stack will have n elements in the worst case scenario. So that's why we are saying that the space complexity will be order of n, because we are referring to the auxiliary space. So yeah, like the video, subscribe the channel. If you have some kind of question that you would like me to target, or you have some kind of topic that you would like me to talk about, then just let me know in the comments. Now we will meet in the next video. Till then, bye.